All right, so this is an optional part of section 2.3, and everybody really should look at this. I shouldn't call this optional, but it's not um, as important as the rest of the sections. So I'm just giving you this as a third segment. But let's prove the thing that I was talking about. Limit of sine of x over x as x approaches 0 is equal to 1. Now I'm going to use theta for x. So this is of course the same thing because I'm using theta as an angle in this picture, and theta is a better symbol for an angle because x could mean like the x coordinate or something. All right, so let's see what we have here. Okay, so now you find the area of the triangle OAC. AOC. Wow, sounds like a congresswoman. Triangle AOC. So that triangle AOC, right? So you have this area of the triangle that you can see is less than the area of sector OBC. Now you say, what in the world is a sector? Okay, the sector is a piece of pie. So here you can see OBC like that in the picture, right? So it's right here. It's a piece of pie that's cut by this, this cut OD. So that is the piece of pie OBC, and that is, you can see, it's less than the area of this triangle, the outside triangle OBD. Okay, so what am I saying? I'm saying this is less than the piece of pie, less than the bigger triangle, where the smaller triangle is like this. Okay, that's all I'm saying. OAC is less than the piece of pie OBC, which is less than, actually it's strictly less than. But the point is, I'm using the sandwich theorem, okay, so this is OBD. Okay, you get that? So this sets up the squeeze theorem. I am trying to find something inside. Well, of course, that's not yet. This is what I'm looking for. But soon we'll find that this is how you can prove that limit is equal to 1. Okay, so let's find the area of AOC. Okay, how do you do that? AOC, well, that is 1/2 times this, the base. Well, what's a base? That's OA, but that's a cosine of theta. And how about the height? That's AC, but that's a sine of theta. Duh, right? I mean, it's a sine, cosine. It's the first picture you have learned in trigonometry, maybe. All right, so that's that. No problem here. Okay. The second one, the triangle, well, the third one actually, OBD. Okay. Now, OBD is an interesting one because it's 1/2, right? And what is OB? Well, OB is actually the radius of this unit circle. That's 1. Okay. Now, what is dB? You notice here, dB can be written as dB over 1, right? dB over 1 is the tangent of theta. Why is this a tangent? Well, that's because it's the opposite over hypotenuse, right? dB is the opposite of theta. OB is the, opposite over the adjacent. OB is the adjacent, and OB has length 1. So that is the tangent. So in other words, dB is actually length, which represents the tangent of theta. Okay, so that's no problem, right? So this is 1/2 times the base times height. This is also 1/2 times the base times height. A tricky thing is this one, the sector. Okay, so sector OBC, you have this theta. This is theta over 2 pi. Now, this is the proportion out of the entire circle, right? If theta is 45 degrees over 360, that's the proportion of this sector, the piece of pie, relative to the whole circle. Now, you know what the whole circle area is? The area of the entire circle of radius 1 is pi r squared, where r is equal to 1. So that's pi times 1 times 1, which is pi. So the entire circle is pi, but we're only taking a small piece, which is represented by theta over 2 pi. And that's because this angle is theta, and the entire circle has the central angle of 2 pi, right? So theta over 2 pi is the percentage of the entire circle, which has the area pi. Well, you can cancel this. So it's really easy to find the sector area of OBC, which happens to be theta over 2. Right, I am saying this is less than that, which is less than this, right? So let's go ahead and write this. 1/2 cosine theta, sine theta, less than or equal to, actually it's less than, right, as you see in the picture, but who knows, as theta gets closer and closer, maybe they get really close. So I'm just going ahead and using less than or equal to, even though the equal to part is not necessary. All right, so this is what I get. 1/2 is a positive number. I can just get rid of that, okay? And so what we have here on the next page is cosine theta, sine theta, less than or equal to theta, less than or equal to tangent theta. All right, let's divide everything by cosine, sine. Okay. Now, note that sine of theta is positive in this picture, right? So, and by the way, theta, we don't allow theta to be exactly 0 because notice here, we are trying to find the limit as theta approaches 0, so it's not 0. So sine is, sine of theta is 0, and so you divide. So divide everything by sine of theta. So what do you get? You get cosine of theta less than or equal to theta over the sine of theta less than or equal to the tangent. Or by the way, tangent is sine over cosine. Right? So if you divide this by sine of theta, you get 1 over cosine of theta. Okay, as theta goes to 0, guess what? This goes to 1, this goes to 1. And therefore, by the squeeze theorem, what's sandwiched between 1 and 1 is going to be 1. So the limit of theta over sine of theta is going to be 1. Okay, so this is a direct application of the squeeze theorem. Now, notice here, sine theta over theta is simply 1 over this expression. It's basically the reciprocal, right? And this approach is 1. So the reciprocal also approaches the reciprocal of 1, which is 1. So that means the limit of sine theta over theta, which is the reciprocal of this, as theta approaches 0 is equal to 1. Basically, what this is saying is theta and the sine of theta approach 0 at about the same ratio or at the same speed. And that's why the limit is going to be 1. All right, so that's a nice application of the theorem. Now, you may wonder, what happens if theta is negative? Okay, well, in the theta is negative, then the area is actually going to be negative. It's a little more complicated, but you could also prove that even if sine of theta is negative, okay, approaching 0 from the negative side, you could come up with a similar argument, and you would see that this limit is also going to be 1. All right, so now consider the second one. All right, the second one says 1 minus cosine of x over x, right, as x approaches 0. Right, so what can you do with this? Well, this one, you could actually use the previously discussed method, which is multiply by its conjugate on the top and the bottom. Okay, all I did is to multiply this by 1, which is written as 1 plus cosine of theta, cosine of x, over 1 minus cosine of x. So this will be 1 minus, remember, cosine square of x on the top, and on the bottom, nothing changes. Okay, but notice what the top is, right? It's sine square of x, because 1 minus cosine squared, as you know, is sine squared. And at this point, I still can't plug in 0 for x because you have 0 over 0, but you can write sine square as sine x times sine x. And you can separate this into two fractions, sine x over x, which we know something about because we just saw that right here, right? So this actually approaches 1 when you take the limit. Okay, so as x approaches 0, this goes to 1. And what is this? This is 0 over 1, right? Which is 0. Okay, so the point is this first part approaches 1, this approaches 0, and therefore, now I didn't write the limit notation. Oh, this 3 dots means therefore in mathematics. I'm about to write the conclusion. The limit of 1 minus cosine of x over x as x approaches 0 is going to be the limit of this guy times the limit of this guy, which is 1 times 0, which is 0. Okay, and that is the second thing I showed you before at the end of the segment 2 of our video on section 2.3. All right, now these two, you may wonder why we are looking at these two specific limits, and the reason is because both of these will play a major role when we try to do calculus on trigonometric functions. All right, so until then, you just want to remember this. You don't have to remember the proof of these, but you can remember that these limits do exist. All right, so that concludes our discussion on 2.3.